For example 4, we're skipping a little bit just for time's sake and also technology's sake. For example 4, we're dealing with two rockets here. We got rocket 1 is launched from the ground, and its height is modeled by the function f of x equals negative 16x squared plus 120x. Rocket 2 is launched from the ground a few seconds later, and its height is modeled by the function g of x equals negative 16x squared plus 248x minus 736. We're asked to answer the following questions. But before we answer any questions, maybe we should plot this in our graph. So first function, negative 16x squared plus 120x. For the second function, we've got negative 16, not negative 13, negative 16x squared plus 248x minus 736. So when you graph this, your graph probably ends up looking a little bit like this, which doesn't do you a whole lot of good. You can kind of see like one part of a graph that kind of looks like the downward side of a parabola. Then you've got another one, maybe that's an upward side of the parabola. I'm saying that obviously because I also know what the graph looks like, so it's not fair of me to do that. We got to change the window. A couple things we're going to pay attention to. We don't really care about the left side here because our x-axis is time. So we're not worried about like negative time. You're not worrying about before the rocket launches, how high is it? That doesn't make any sense. So let's go to our window. Let's do our x min of 0 because again, we don't really care about negative time. Let's do an x max of 20. That should be more than enough. So if we graph that, we might be able to see a little bit more, but we're going to figure out we're going to need to do even more adjusting to our window. So now you can see, oh, there's a second line there. So I happen to know, and again, I've done this problem a couple times before, that this part here connects with this part here. It's a parabola that's going to open up and come back, or sorry, opens down, starts going up there and comes back down. So we got to adjust our window a little bit, and we're going to have to go pretty high up. Let's do a y max of 500. Now, we don't really care about negative height because we're not worried about the rocket going below ground. But just so that we have a little bit of wiggle room at the bottom, so that way when we're typing things, it's not going to cover up parts of our graph, let's go down to negative 200, just so we can make sure that we see everything. So when we graph it, it looks a little something like this. So now you see the rocket 1 curve and then rocket 2 curve. Cool. Now we're set up to answer the following questions. The first question says, what's the maximum height achieved by rocket 1? So to figure out the maximum, we've done this before, but we'll do second trace maximum. And left bound, well, we got to make sure it's to the left of that coordinate right there, that left of that vertex right there. Right now my cursor there was all the way off to the right for some reason. But we're going to take it, so our maximum is right about there, but for the left bound, again, you got to make sure it's obviously to the left of it. Hit enter. Put your cursor obviously to the right of it for the right bound. Hit enter. Put your guess kind of close to it. Hit enter, and then it gives us some information. It gives us an x coordinate of 3.75 and a y coordinate of 225. This one's just asking for our height. So we're going to say it's got a max height of 225. Now, I didn't include the units anywhere in this example problem, but one thing I happen to know is this is the half of the acceleration due to gravity. Now, when you're thinking about physics, you might be thinking of 9.81 is the acceleration due to gravity. This one's in feet per second squared. It's not an ideal unit. Typically, I strongly encourage the metric system, but for the simplicity of this problem, the imperial system works out well for us. So this is going to be 225 feet. Now for rocket 2, we're going to repeat the same process. We can do second trace maximum. Again, instead of having to click all the way down to like hitting your up and down arrows, you can just type 4. But you'll see right now I'm on the wrong curve. Like if I go over to the right, I'm still in the wrong curve. To get to the correct curve, you hit either up or down on your arrows and it'll jump to a different function. So since we only have 2 functions, it'll jump to the other one. So we want to make sure it's obviously to the left of that maximum point. Hit enter. Obviously to the right of that maximum point. Hit enter. And put your guess kind of close to where it is. And you end up with 7.75 and then 225. So again, we're only curious about the y value. So again, it reaches the maximum height of rats, 225 feet. Now it says, at what point in time are the 2 rockets at the same height? How many seconds into launch is this? So we're looking for the intersection. We haven't done this yet, but if we press second trace, and there's an option number 5 here for intersect, we're going to choose that. And we're going to say, it's going to say first curve, and we're going to use the first parabola, you know, the y1 equals negative 16x squared plus 120x. And we're going to put our first curve cursor pretty close to where they intersect and hit enter. Now you'll see after you hit enter, it jumps to the second curve. So we're going to hit enter again, and we're going to put our guess kind of close to it, and it gives us the value of 5.75 and 161. So it's going to be at 5.75 seconds, and it's at a height of 161 feet. So if they were launched from the exact same spot and they're following the exact same trajectory, they'd run into each other. Now, we're assuming that they're not going to run into each other. They're launched from two different launch pads, so nothing to worry about there. For question 4, it says, how long does it take for Rocket 1 to land? Well, Rocket 1, it launches at 0 seconds, and we're going to have to figure out where it lands there. So we're going to figure out the 0 there. So if we do second trace, and option number 2 is 0. It's still weird to say 2 is 0, but that's what it says. And we're going to put our left bound close to that 0 there, but a little to the left of it. In this case, left happens to be above it. Hit enter. Then we're going to move it a little to the right of it. In this case, right happens to be below it. Hit enter. And put your guess kind of close to it. And you'll see it lands at 7.5 seconds. So it starts off at 0, ends at 7.5 seconds. Now we're going to do the same thing for Rocket 2. We'll do second trace, and we're going to do, option number 2 again for 0. And let's find that point over there. Now I'm on the wrong curve right now, so I'm going to hit up. Put the left bound close to it, but still to the left of it. Hit enter. Put your right bound close to it, but still to the right of it. Hit enter. Put your guess kind of close to it. Hit enter. And you'll see it's 11.5. Now, this rocket, that says number 1. This rocket does not go in the air for 11.5 seconds because it doesn't start off at time equals 0 and land at 11.5. It starts off whatever at this time is. So we got to figure out that time as well. So if we do second trace 0, we got to do the same thing. Find our cursor again. There we go. Switch to the other function. We got to do the same thing, but we got to figure out what that 0 is. So we'll do left bound. In this case, left happens to be below it. Hit enter. We'll do right bound. Right happens to be above it. Hit enter. Put your guess kind of close to it, and it's at 4 seconds. So this is launching 4 seconds after the other one. So it lands after a total of 11.5 seconds, but it launches 4 seconds in. So we're going to do 11.5 minus 4, which gives us 7.5 seconds. So even though these are two different functions, they end up giving us pretty similar information.